Tonight, imagine you are standing outside on a clear night, looking up. Somewhere beyond the stars you can see, beyond the galaxies you cannot. There is an edge. The edge of everything we can observe. Everything our instruments have ever touched. It sits 46.5 billion light years away in every direction. But here is the truth that scientists rarely say out loud. Nothing will ever reach it. Not a spacecraft, not a signal, not a beam of light fired from Earth tonight aimed directly toward it. The universe expands faster than anything can travel, and the edge moves away from everything, always, without exception. This is not a problem waiting to be solved. It is the shape of the universe we live inside. If you enjoy long-form space content, the kind made for quiet nights and open minds, do me a small favor and hit the like button and subscribe. It genuinely helps this channel reach more people who need exactly this kind of thing. Make yourself comfortable. Let's begin. On the clearest night you will ever experience, far from any city, lying on your back in a field, eyes fully adjusted to the dark, the human eye can resolve approximately 5,000 individual stars. 5,000 points of light scattered across the full dome of the sky, horizon to horizon. It feels like an overwhelming number. It feels like more than anyone could count. And yet 5,000 stars, out of the 200 to 400 billion stars estimated to exist in the Milky Way alone, is a fraction so small it barely registers as a fraction at all. It is closer to nothing than to something. You are seeing, on the most generous possible night, roughly one star out of every 80 million that exist in your own galaxy. The rest are invisible, too distant, too dim, too buried behind the thickness of gas and dust that fills the galactic plane. The sky feels full. The sky is, by any honest accounting, almost entirely hidden from you. And yet the feeling of fullness persists. It has persisted across human history with remarkable stubbornness. For most of the time our species has existed, the sky was the primary evidence that the universe was dense, inhabited, and generous. Ancient cosmologies filled the heavens with structure, crystalline spheres nested inside one another, each carrying its cargo of stars, the whole arrangement packed and purposeful and close. The Greeks imagined the stars embedded in a solid vault, a ceiling of fixed lights rotating overhead. Medieval astronomers placed Earth at the center of a series of concentric shells, each shell occupied, each gap filled with some form of celestial substance. The universe, in almost every early model, was assumed to be full. Emptiness was considered unstable, even philosophically suspect. Nature, it was said, abhors a vacuum. The default assumption was presence, not absence. It took centuries of careful observation to begin dismantling that assumption, and even then, it dismantled slowly. The telescope arrived in the early 17th century, and for a time, it seemed to confirm the feeling of fullness. Galileo turned his instrument toward the Milky Way and found that what appeared to the naked eye as a faint, continuous smear of light resolved into stars. Thousands of them, then tens of thousands. The sky was not merely full. It was more full than anyone had imagined. Each improvement in optics revealed new layers of stars behind the ones already visible, and the impression of density deepened. What took much longer to understand was that this impression was an artifact of looking, not a fact about the universe. The stars visible through any telescope, however powerful, represent only those close enough and bright enough to register. The vast majority of stars in the Milky Way are invisible to us, not because they are few, but because the galaxy is large, beyond easy intuition, and most of its contents lie at distances where individual stars blur into background glow or disappear entirely. The thickness of gas and dust along the galactic plane, the interstellar medium, absorbs and scatters light, hiding entire regions from optical observation. For centuries, astronomers looked at the Milky Way and saw only the nearest arm of it, a thin slice of a structure that extends 100,000 light-years across, and concluded they were seeing something close to the whole. The full picture emerged slowly through the 20th century as radio telescopes, infrared instruments, and eventually space-based observatories began mapping the galaxy at wavelengths that could penetrate the dust. What they found was a spiral galaxy of extraordinary size and relative thinness, a flat disk roughly 1,000 light-years thick at the edges and perhaps 12,000 light-years thick at the central bulge, rotating slowly, containing somewhere between 200 and 400 billion stars. Our Sun sits roughly 26,000 light-years from the galactic center, about halfway out along one of the spiral arms. We are not at the center of anything. We are in the middle of the disk, in a moderately populated neighborhood, surrounded by stars we cannot see with the naked eye, and separated from the galactic core by a distance that light itself needs 26,000 years to cross. Consider what that means for the 5,000 stars visible on your clearest night. Each of those stars is a near neighbor, cosmically speaking. Most are within a few hundred light years. A handful are within 50. They cluster in the narrow cone of the galaxy that happens to surround our position in the disk. They are not a representative sample of the Milky Way. They are the local block. They are the view from a single window in a city that extends for thousands of miles in every direction, and the city is not dense. This is the part the feeling of a full sky consistently obscures. The Milky Way contains hundreds of billions of stars, and it is also enormous, so enormous that those hundreds of billions of stars are spread across a volume of space so vast that the average distance between any two neighboring stars is measured in light years, not miles, not kilometers, not the distances we use for anything in ordinary life. Light years. Each star is separated from its nearest neighbor by a gap that light, moving at nearly 300,000 kilometers per second without stopping, needs years to cross. The stars feel close because we see them all at once, projected onto the flat screen of the sky with no depth, no sense of the three-dimensional distances collapsing into a single image. A star 500 light-years away and a star 50 light-years away appear side by side in the same patch of sky, and the mind assigns them the same proximity. They are not close. They are not even in the same neighborhood. The sky is a map that has lost all its distance information. What we are left with when we look up and feel abundance is an illusion constructed from a combination of factors that all point the same direction. Biology limits us to the visible spectrum, hiding the majority of stars from our eyes entirely. Atmosphere blurs and scatters light, softening the distinction between stars and background. Distance collapses in two-dimensional projection, making remote objects appear adjacent. And the human visual system, shaped by evolution to find patterns and presence in its environment, interprets any field of bright points as a full and occupied space. Every one of these factors inflates the apparent density of the sky. The universe does not correct for these factors. It simply is what it is, which is to say, mostly not there. There is one more layer to the illusion that is worth naming before we go further, because it reaches deeper than optics and biology. It reaches into the matter itself. Even the stars we can see, the ones close enough and bright enough to register as points of light in our instruments, are not the solid, dense objects they appear to be. A star like our Sun is a sphere of plasma, roughly 1.4 million kilometers across. It is enormous by any human standard. And yet the atoms that make up that sphere, the hydrogen and helium that constitute nearly all of its mass, are themselves almost entirely empty. The nucleus of a hydrogen atom is so small relative to the atom as a whole that if you were to scale the atom up to the size of a football stadium, the nucleus would be roughly the size of a marble sitting at the center. And between that marble and the outermost reaches of the electron cloud surrounding it, nothing. Empty space, in proportions that have no comfortable analogy in ordinary experience. The star you are looking at is not solid. Planet you are standing on is not solid. The hand you might be resting beneath your head as you listen to these words is not solid, not in the way the word solid usually implies. It is matter arranged in patterns dense enough to resist other matter's attempts to occupy the same space. But the atoms themselves are mostly void, and the structures those atoms assemble into are mostly void, and the galaxy those structures are scattered across is mostly void, and the universe that contains the galaxy is mostly void. The night sky looks full. Every layer of examination reveals it to be emptier than the layer before. The further in you look, the less is there. The further out you look, the less is there. The feeling of fullness is the first thing to go when the numbers arrive. And the numbers are only just beginning. We have been describing how the sky looks and why it looks different from what it is. We have not yet asked the harder question: what empty actually means, when physics is permitted to define it precisely, because the definition that physics offers is stranger than the intuition suggests. It is not simply the absence of things. It is something the universe does actively, on a scale that makes the gaps between stars seem almost intimate by comparison. The word empty carries a simple meaning in ordinary life. An empty room has no furniture. An empty glass has no liquid. Empty means the absence of the things that are supposed to be there. It is a temporary condition, a container waiting to be filled. We use it casually, without much weight, because in the world of human experience, true emptiness is rare and brief. A room is empty before the furniture arrives. A glass is empty before the water is poured. Emptiness, in this sense, is a transitional state. It does not last. Physics uses the same word, but it means something different, something older, and considerably stranger. In physics, a vacuum is not merely a space that happens to lack furniture. It is a precisely defined state, a region of space with a particle density low enough that the particles present have no meaningful effect on the physics occurring there. By that definition, most of the universe is vacuum. Not some of it. Not the spaces between the interesting parts. Most of it. The vacuum is not the background against which the universe happens. The vacuum is the universe, interrupted occasionally by small, improbable clumps of matter that we have given names to. To understand how empty the emptiness really is, it helps to move through a series of comparisons. Start with the air in a room. At sea level, a single cubic centimeter of air, a space about the size of a sugar cube, contains roughly 27 million trillion molecules. That number has 19 digits. The air feels thin to us. We cannot see it, cannot grasp it. And yet it is, by the standards of the universe, extraordinarily dense. It is a crowd. It is a traffic jam. It is matter packed together at a concentration that almost nowhere else in the observable universe approaches. Move outward. The best laboratory vacuum humans have ever achieved, produced in specialized chambers for particle physics experiments, using vacuum pumps and elaborate cooling systems, reduces the particle count in that same cubic centimeter to roughly 10 million molecules. Still 10 million. Still a crowd by cosmic standards, but a fraction of what fills the air around you. The engineers who build these chambers consider them extraordinarily empty. They are the closest to nothing that human technology has managed to produce. Now move to low Earth orbit, a few hundred kilometers above the surface. The atmosphere has thinned dramatically. A cubic centimeter of space at that altitude contains somewhere between 100,000 and 10 million molecules, depending on solar activity and altitude. It is thin enough that satellites experience only the faintest atmospheric drag. But there is still something there, still a presence. Move further out, beyond the atmosphere entirely, into the space between planets. The interplanetary medium, the diffuse gas and dust threaded through the solar system, carried outward by the solar wind, contains perhaps 5 to 10 particles per cubic centimeter. Not millions, not thousands. 5 to 10. A cubic centimeter of interplanetary space holds roughly the same number of particles as a sugar cube of air, holds molecules in the digit furthest to the right of that 19-digit number. The ratio is staggering, but it is not yet the bottom. Move beyond the solar system into interstellar space, the space between the stars. Here, the density drops again, dramatically. The average density of the interstellar medium in our region of the galaxy is roughly 1 atom per cubic centimeter. 1. A single hydrogen atom, on average, occupying a space the size of a sugar cube. In the denser regions, inside molecular clouds, where new stars are forming, the density might climb to 10,000 atoms per cubic centimeter, which still falls far below the best vacuum ever produced in a laboratory. The densest naturally occurring clouds of interstellar gas are emptier than anything human technology has manufactured. What we call a cloud, in the interstellar context, would register as a hard vacuum in any physics department on Earth. And that is still not the bottom. Move beyond the galaxy into intergalactic space, the vast regions between galaxies. Here the density falls to approximately 1 atom per cubic meter. Not per cubic centimeter, per cubic meter. Cubic meter is a space roughly the size of a large washing machine. In intergalactic space, that volume contains, on average, a single atom. 1 hydrogen atom, drifting in a cube of darkness with sides a meter long, with nothing else nearby. This is as close to absolute nothing as the observable universe permits. It is an emptiness so complete that it has no human analogy, because nothing in human experience approaches it. The best vacuum a laboratory can produce contains 10 million times more matter than intergalactic space. What this means in practice is that if you were somehow transported to a random location in the universe, not to a planet, not to a solar system, not even to a galaxy, just to a random point in space, chosen without bias, you would almost certainly find yourself in intergalactic void. You would see nothing nearby. You might, at enormous distances, detect the faint smear of a galaxy, but in any direction you could reach within a human lifetime. Even traveling at speeds that dwarf anything we have built, there would be nothing. No atom close enough to touch, no particle close enough to interact with, just the darkness and the slow drift of a single hydrogen atom every cubic meter, and the faint background radiation left over from the beginning of the universe, cooling toward absolute zero. This is the universe's default condition. Not planets, not stars, not galaxies. This, the near-perfect vacuum of intergalactic space, is not the exception. It is the rule. Everything else, every galaxy, every nebula, every ocean and mountain and living cell, is the exception. It is worth pausing on that inversion, because it runs against every instinct. We think of space as the background and matter as the foreground. We think of the stars as the thing, and the darkness between them as the absence of the thing. But by volume, by any measure of spatial extent, the darkness is not the background. The darkness is almost everything. The stars are barely a footnote. And then physics offers one further complication, one more layer beneath the emptiness. And it is the strangest of all. Even in regions of space with no particles at all, not one hydrogen atom per cubic meter, not one particle of any kind, the space itself is not truly empty in the deepest sense. Quantum mechanics predicts, and experiments have confirmed, that the vacuum seethes with activity at scales far below anything directly observable. Virtual particles, pairs of matter and antimatter, flicker into existence and annihilate one another in intervals so brief they cannot be directly detected, only inferred from their effects on nearby matter. This is called the quantum vacuum, and it carries energy. Not much, but measurable. The Casimir effect, a faint attractive force observed between two uncharged metal plates placed extremely close together in a vacuum, is one of its signatures. The plates are being pushed together by the pressure of virtual particles, by the energy of empty space itself. What this means is that there is no such thing as absolute nothing. The universe does not permit it. Even the most perfectly evacuated region of space is threaded with quantum fluctuations, with the faint energetic hum of virtual processes occurring and dissolving below the threshold of ordinary matter. The void is not silent. It is active. It is restless. It merely contains nothing we can hold or see or reach. This is the universe's floor, the lowest level of emptiness it will allow. And it is still, by every meaningful measure, almost perfectly vacant. The quantum vacuum's energy is real, but diffuse beyond any useful analogy. It does not warm you. It does not slow you. It does not provide any resistance to your passage through it. For all practical purposes, it is nothing. For all philosophical purposes, it is the closest the universe comes to nothing without quite arriving. And so we have a picture that is already deeply strange, before we have looked at any specific object or structure in the universe. Empty space is the dominant fact of existence. The vacuum is not a gap between things. It is the thing itself. Matter is an intrusion. Life is a local improbability. The universe is not full of stars the way a jar is full of marbles. It is full of emptiness the way an ocean is full of water. and the stars are scattered through it the way a handful of sand is scattered across the surface of the Pacific. Rare, isolated, impossibly far apart, and dwarfed in every direction by the depth and extent of the void surrounding them. We have been talking about empty space. We have not yet talked about the matter that fills what little space it occupies. Because matter, it turns out, has its own emptiness, a hollowness at its core that makes the interstellar void seem almost dense by comparison. And to understand that hollowness, we have to go to the smallest scale physics can reach and look at what solid things are actually made of. In the autumn of 1909, in a laboratory at the University of Manchester, a physicist named Ernest Rutherford directed two of his students, Hans Geiger and Ernest Marsden, to perform an experiment that everyone involved expected to be straightforward. The experiment was simple in design. A thin sheet of gold foil, only a few atoms thick, was placed in the path of a beam of alpha particles, small, positively charged fragments of matter emitted by radioactive materials. A detector screen surrounded the foil, designed to register where the particles landed after passing through. The expectation, based on the dominant model of the atom at the time, was that the particles would pass through the foil with only minor deflections, like bullets passing through a cloud of fine mist. Matter, in the prevailing view, was a soft and uniform thing, a diffuse pudding of positive charge with electrons embedded throughout, too spread out and gentle to significantly redirect anything moving quickly through it. What happened instead quietly dismantled that picture of reality. Most of the alpha particles did pass straight through, as expected, but some deflected at large angles, and a small number, roughly 1 in 8,000, bounced almost directly backward, as if they had struck something solid and immovable, buried within the foil. Rutherford later described his reaction with characteristic understatement. It was, he said, as if you had fired artillery shells at tissue paper, and they had bounced back and hit you. The result was so unexpected that it took him nearly 2 years to accept what it implied. What it implied was that the atom is not a soft, uniform cloud. It is almost entirely empty space, with nearly all of its mass concentrated in a vanishingly small central nucleus. The alpha particles that passed straight through had missed the nucleus entirely, sailing through the vast emptiness of the atom without encountering anything. The few that bounced back had scored a direct hit on the nucleus, an event so rare because the nucleus itself is so extraordinarily small relative to the total size of the atom. How small? The numbers are difficult to hold, but they are worth attempting. A hydrogen atom, the simplest atom, consisting of a single proton and a single orbiting electron, has a diameter of roughly 1/10 of a nanometer. A nanometer is 1/1000th of a meter. 10 million hydrogen atoms placed side by side would span approximately 1 millimeter. The atom is small beyond any useful visual anchor. But the nucleus of that hydrogen atom, the single proton at its center, is roughly 100,000 times smaller than the atom itself. 100,000 times. If you were to scale a hydrogen atom up to the size of a large cathedral, a space perhaps 100 meters across, the nucleus at its center would be approximately the size of a marble. A single marble, sitting at the center of a vast stone hall, and between that marble and the outermost reaches of the electron cloud at the cathedral walls, nothing. No furniture, no air, no particles of any kind, just empty space, held in shape by electromagnetic forces, so abstract they have no texture, no color, no presence that any sense organ could register. This is what matter is made of, not solidity, not density. A marble in a cathedral, repeated across scales that comprehension cannot fully reach. Consider what that means for the objects around you: the chair, the floor, the walls. Every solid thing in your immediate environment is constructed from atoms, and every one of those atoms is a cathedral with a marble at its center. The solidity you feel when you press your hand against a surface is not the solidity of packed matter. It is the solidity of electromagnetic repulsion. The electrons in the atoms of your hand, pushing back against the electrons in the atoms of the surface, two clouds of negative charge refusing to occupy the same space. You are not touching the table. Your electrons are repelling its electrons at a distance so small it feels like contact, but is not. Nothing in the physical world touches anything else, not in the way the word touch implies. Every sensation of contact is a long-range electromagnetic conversation between clouds of charge, conducted across distances that are, at the atomic scale, enormous. To put this in human terms, the matter in your body is almost entirely empty space. Your body contains roughly 7 billion atoms. That is a 7 followed by 27 zeros. Each one of those atoms is a cathedral with a marble. If you were somehow able to remove all the empty space from every atom in your body, compressing each nucleus and each electron into direct contact with one another, the resulting object would be roughly the size of a single grain of fine sand. All of you, every cell, every memory, every year of experience and growth and learning, compressed into a speck, barely visible to the naked eye. And the same is true of every other human being who has ever lived. If you gathered every person who has ever existed, estimates range from around 100 billion individuals across all of human history, and removed the empty space from all of them simultaneously, the compressed result would fit comfortably inside a cube, roughly the size of a sugar cube. 100 billion lives, all of human history, reduced to something you could hold between two fingers. What this means is that the solidity of the world is a functional illusion, not a deception. The electromagnetic forces that create the impression of solidity are real, and they have real consequences. You cannot walk through walls because the electron clouds in the wall's atoms genuinely repel the electron clouds in your body's atoms. The repulsion is physical. The resistance is measurable. But the resistance is not caused by matter being densely packed. It is caused by force fields surrounding matter that is, itself, almost entirely absent. Rutherford's experiment in 1909 was the moment this became undeniable. Before that experiment, the emptiness of matter was not yet known. After it, there was no longer any intellectually honest way to look at a solid object and believe it was what it appeared to be. The table is not solid. The floor is not solid. The planet beneath you is not solid, not in the deep sense. It is a vast collection of atomic cathedrals, each one almost entirely empty, assembled into structures large enough to have gravity, warm enough to support liquid water, dense enough in aggregate to resist your weight, but hollow at every level of examination, all the way down. This is where the emptiness of the universe becomes personal rather than astronomical. The scale of the cosmos is difficult to feel. The distance to the nearest star is a number, not an experience. But the emptiness of matter is closer. It is in your hand right now, in whatever surface you are resting against, in every breath of air moving through your lungs. You are made of the same emptiness you have been contemplating in the night sky. The atom is not a small version of a planet, dense and filled. The atom is a small version of the solar system, a central mass surrounded by an enormous relative void, with the outer boundary defined not by solid walls, but by the reach of invisible forces. And the solar system, it turns out, is the next scale at which this pattern repeats. Because if the atom is a cathedral with a marble at its center, the solar system is something larger still, a structure so vast and so sparsely occupied that the emptiness of the atom begins to feel almost intimate by comparison. We think of our solar system as a neighborhood, a collection of planets and moons and asteroids arranged around a central star, close enough to one another to be mapped on the same diagram, close enough that we have sent spacecraft to visit most of them within a human lifetime. But the diagram lies, as all diagrams of the solar system must lie to fit on a page. The distances involved are not neighborly. They are not even in the same category as the distances we use for anything on Earth. And when you replace the diagram with the actual numbers, the solar system dissolves, like the atom before it, like the matter inside the atom before that, into something that is almost entirely and uncomfortably nothing. There is a model of the solar system that exists in almost every science classroom in the world. A yellow sphere at the center, representing the sun. A series of smaller spheres arranged in a neat line extending outward. Mercury, Venus, Earth, Mars, then the gas giants, then the distant ice worlds at the edge. The spheres are different sizes. The gaps between them vary. But on the page, or on the wall, or in the plastic model, rotating slowly on a teacher's desk, everything feels proximate. Everything feels arranged. The solar system, in this rendering, looks like a populated place, a system, a neighborhood with residents. The model is useful for memorizing the order of the planets. It is deeply, almost comically misleading about everything else. The first thing the classroom model gets wrong is scale. To represent the solar system accurately, with the sun and planets drawn to their true sizes and their true distances from one another, you would need a space so large that the exercise becomes impractical almost immediately. If you placed a grapefruit on the ground to represent the sun, Mercury would be a grain of sand, roughly 18 meters away. Earth would be a small pea about 48 meters from the grapefruit. Mars would be another small grain of sand, roughly 73 meters out. So far, the model fits in a large parking lot. But then the distances expand rapidly. Jupiter, a marble in this scale, would be 250 meters from the grapefruit, 2.5 city blocks. Saturn, slightly smaller, would be nearly half a kilometer away. Uranus would be over a kilometer out. Neptune, the outermost major planet, would sit roughly 3 kilometers from the grapefruit sun. And in between all of these objects, between the grapefruit and the grain of sand that is Mercury, between the marble of Jupiter and the slightly smaller marble of Saturn, between every planet and every other planet, nothing. No other objects at the correct scale. No asteroids visible. No comets. Just open ground, extending in every direction, with tiny objects separated by distances that require walking to appreciate. 3 kilometers from the sun to Neptune. That is the solar system, at grapefruit scale. A handful of small objects, the largest no bigger than a marble, spread across a circle 6 kilometers in diameter. And the nearest equivalent grapefruit, the nearest star, would be, at this same scale, approximately 13,000 kilometers away, roughly the distance from London to Sydney and back again. In between, nothing at the scale of this model, not one object of any significance, just the empty ground of the scale model, extending for a distance that no human could walk in a lifetime. This is the solar system, not the diagram. This, the actual numbers, confirm what the scale model suggests. The distance from the Sun to Neptune is approximately 2.8 billion miles. Light, moving at nearly 300,000 kilometers per second, takes roughly 4 hours to cover that distance. A radio signal sent from Earth to a spacecraft near Neptune takes 4 hours to arrive and 4 hours to return. Mission controllers communicating with the Voyager probes near and beyond Neptune's orbit in the 1980s waited the better part of a day for a round-trip exchange. The solar system is, by the measure of light itself, hours across, and light is the fastest thing that exists. Now consider what fills that space. The Sun contains approximately 99.86% of all the mass in the solar system. Everything else, all 8 planets, all their moons, the asteroid belt, the Kuiper belt objects, the comets, the dust, the solar wind, the debris of 4.5 billion years of planetary formation, accounts for the remaining 0.14%. And even that 0.14% is not gathered in one place. It is distributed across a volume of space so vast that the objects themselves are separated by distances that dwarf the objects entirely. The asteroid belt is perhaps the most commonly misrepresented structure in the solar system. In science fiction, it appears as a dense field of tumbling rocks, a hazard to be navigated with care, a wall of debris that spacecraft must thread through cautiously. The reality is almost the opposite. The asteroid belt occupies a region of space between Mars and Jupiter, a broad band stretching from roughly 2.2 to 3.2 astronomical units from the Sun. An astronomical unit being the average distance from Earth to the Sun, approximately 93 million miles. The belt is enormous, but the objects within it are sparse beyond any comfortable analogy. The average distance between asteroids in the belt is roughly 600,000 miles. 600,000 miles between neighbors. The belt contains an estimated 1 to 2 million asteroids larger than 1 kilometer across, and yet the total mass of all of them combined is less than 4% of the mass of the Moon. They are tiny objects, separated by vast distances, distributed through a volume of space so large that every spacecraft ever launched through the asteroid belt, Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, New Horizons, and others, has passed through without incident, without coming close to striking a single object. The hazard does not exist. The density is not there. The belt is a name given to a region of space that is, by any honest measure, almost entirely empty. Beyond Neptune, the Kuiper belt extends from roughly 30 to 50 astronomical units from the Sun, a region even broader than the inner solar system, populated by icy objects, dwarf planets, and the frozen remnants of the early solar system. Pluto resides here. So does Eris, Makemake, and dozens of other named bodies. And yet the Kuiper Belt, despite containing perhaps trillions of small objects, is so vast in extent that the density of material within it is extraordinarily low. The objects are real, but the space between them is the dominant fact. And beyond the Kuiper Belt, the solar system does not end. It fades. The Oort cloud, a theoretical shell of icy objects extending from roughly 2,000 to 100,000 astronomical units from the Sun, represents the outermost boundary of the Sun's gravitational influence. It has never been directly observed. No telescope has resolved an individual Oort cloud object in situ. Its existence is inferred from the behavior of long-period comets that occasionally fall inward toward the Sun, their paths consistent with originating in a distant, roughly spherical reservoir. The Oort cloud is thought to contain trillions of objects, chunks of ice and rock left over from the formation of the solar system, drifting slowly at distances so enormous that the Sun itself would appear as little more than a bright star from their surfaces. The nearest edge of the Oort cloud is approximately 2,000 astronomical units away, 186 billion miles. The outer edge sits perhaps 100,000 astronomical units out, or roughly 1.6 light-years from the Sun, nearly halfway to the nearest star. And the Oort cloud, across its immense extent, contains trillions of objects, each one tiny, each one separated from its neighbors by distances measured in millions of miles. The fill fraction, the ratio of matter to empty space, is indistinguishable from zero at any scale a human instrument can measure. If you were somehow placed at a random point inside the solar system, not on a planet, not near a moon, just somewhere within the volume of space bounded by the Oort cloud, the probability of being within 1,000,000 miles of any object of any kind would be extraordinarily small. You would most likely find yourself in complete darkness, with the Sun reduced to a point of light indistinguishable in brightness from the nearby stars, surrounded by nothing in every direction, drifting in a silence so complete that the word silence fails to capture it. The solar system is not a populated place. It is a nearly empty volume of space, with a few small objects scattered through it at enormous mutual distances, all of them orbiting a star that is, itself, almost entirely plasma and force and light, with very little of what we would ordinarily call substance. This is the structure we were born inside. This is the neighborhood. And the solar system, sparse as it is, empty as it is, hollow at every level from the atomic to the orbital, is, relative to what lies beyond it, almost extravagantly full. Because outside the solar system's boundary, the Oort cloud's outermost reach, the emptiness does not thin gradually into something worse. It drops, suddenly and completely, into the interstellar void. And the interstellar void is a different quality of absence, one that the solar system's own considerable emptiness barely begins to prepare the mind for. In 1838, a German astronomer named Friedrich Bessel accomplished something that had eluded careful observers for 2 centuries. He measured the distance to a star, not estimated it, not inferred it from brightness or color or position, measured it, using a technique called stellar parallax, the same principle that allows your brain to perceive depth when you close one eye and then the other. The slight shift in apparent position that comes from observing the same object from two different locations. Bessel observed a star called 61 Cygni from opposite sides of Earth's orbit around the Sun, 6 months apart, and measured the tiny angular shift in its position against the background of more distant stars. The calculation was painstaking. The angles involved were almost impossibly small. Fractions of an arcsecond, a unit of angular measurement so fine that a full degree contains 3,600 of them. But Bessel was meticulous, and the result, when it arrived, was not what the intuition suggested. 61 Cygni, one of the nearest stars in the sky, one of the ones selected precisely because its parallax shift was expected to be detectable, was approximately 10.3 light-years away, more than 60 trillion miles. The number sat in the scientific literature like a stone dropped into still water, and the ripples it sent through human self-understanding have not fully settled even now. For the first time, someone had replaced the vague impression of stellar distance with an actual number, and the number was crushing. The nearest stars were not distant in the way mountains are distant, or oceans, or even the moon. They were distant in a way that had no precedent in any human experience, no analogy in any landscape, no equivalent in any journey anyone had ever made or imagined making. Bessel's measurement of 61 Cygni was later refined, and we now know it sits 11.4 light-years away. The nearest star system of any kind, Alpha Centauri, a triple system of which the closest individual star, Proxima Centauri, orbits somewhat separately, lies 4.224 light-years from the Sun, 25 trillion miles. Light, which crossed the distance from Earth to the Moon in 1.3 seconds and reached Mars in minutes, needs 4 years and 3 months to cross the gap between our Sun and Proxima Centauri. A beam of light that left Earth the year you were born has not yet arrived. If you are younger than 4, if you are older, a beam that left Earth when you were a small child is only now reaching the nearest star. And in between, across those 4 years and 3 months of light travel, across those 25 trillion miles of space, what exists? The answer has a name. It is called the interstellar medium, and it is one of the most thoroughly studied near-nothings in science. Astronomers have mapped it with radio telescopes, probed it with spacecraft, analyzed its composition through the absorption lines it leaves in starlight passing through it. We know a great deal about the interstellar medium. What we know, in essence, is that it is almost perfectly empty. The interstellar medium is not a uniform thing. It has regions. In the densest regions, the molecular clouds where new stars are forming, vast cold structures of gas and dust that can span hundreds of light years, the particle density reaches perhaps 10,000 atoms per cubic centimeter. That sounds substantial until you compare it to the air in the room around you, which contains 27 million trillion molecules per cubic centimeter. The densest interstellar cloud is roughly 10,000 trillion times less dense than the air you are breathing. It would register as a hard vacuum in any laboratory on Earth. Scientists call it a cloud. In any earthly sense, it is nothing. Beyond the molecular clouds, in the diffuse regions that constitute most of the interstellar medium, the density falls further. In the warm neutral medium, the phase of interstellar gas that fills much of the space between stars in the galactic disk, the density is roughly half an atom per cubic centimeter. In the hot ionized medium, the low-density plasma that fills the spaces between denser structures, it drops to perhaps 1/100th of an atom per cubic centimeter. In the local bubble, the region of unusually low-density interstellar medium that our solar system happens to be passing through, cavity roughly 1,000 light-years across, carved by ancient supernova explosions, the density is lower still, perhaps 1,000th of an atom per cubic centimeter. A cubic centimeter the size of a sugar cube, containing 1,000th of a single hydrogen atom. An emptiness so profound that no instrument we have built can directly detect the individual particles. Their presence is inferred from their collective, statistical behavior across distances of light years. This is the space between stars, not the dramatic darkness of space fiction, with its nebulae and glowing gas and visible structure. Most of it. The ordinary, unremarkable majority of the gap between any two stellar neighbors. A near-perfect vacuum, threaded with the occasional hydrogen atom, occasionally punctuated by a dust grain, a tiny particle of carbon or silicate, perhaps a few hundred nanometers across, separated from the next dust grain by distances measured in kilometers. The dust is real. In aggregate, across light years of accumulated interstellar medium, it is dense enough to obscure distant stars, to redden their light, to hide entire regions of the galaxy from optical observation. But locally, at any given point in the void between stars, the chance of encountering a dust grain is so small as to be effectively zero. Consider what it would mean to travel through this space. The fastest spacecraft humanity has ever launched is the Parker Solar Probe, which at its closest approach to the Sun reaches speeds of approximately 430,000 miles per hour. It is the fastest thing we have ever built. At that speed, a journey to Proxima Centauri would take roughly 6,500 years. Not decades, not centuries. Millennia. A civilization that launched such a probe at the height of ancient Egypt would be waiting until roughly the year 8,500 for it to arrive. And for the entirety of that 6,500-year journey, the probe would travel through a medium so empty that it would encounter, on average, perhaps a few thousand hydrogen atoms per second, a number that sounds large until you realize that a single breath of air contains more atoms than the probe would encounter across the entire 6,500-year crossing. The void between stars does not thin as you move into it. It simply is what it is, from the moment you leave the outermost reach of the solar system to the moment you approach the outermost reach of the next one. There is no gradient of increasing emptiness. There is no wall you cross. The Oort cloud fades, the sun diminishes to a bright point among other bright points, and the interstellar medium is simply there. Always has been, in every direction, at every point along the journey, as close to nothing as matter-containing space permits. There is a moment in the history of space exploration that carries some of the weight of this distance more quietly than any number. On February 14, 1990, the Voyager 1 spacecraft, then approximately 3.7 billion miles from the Sun, having completed its tour of the outer solar system, turned its camera backward at the request of the astronomer Carl Sagan and photographed the inner solar system from the outside. In the resulting image, Earth appears as a pale blue dot, less than a pixel across, suspended in a beam of scattered sunlight, surrounded by the utter blackness of interstellar space beginning to open around it. Sagan wrote about that image with a stillness that belongs to this register: the Earth as a mote of dust suspended in a sunbeam. Every human being who has ever lived, every civilization, every act of love and war and creation, occurring on a pale dot drifting in the early reaches of an interstellar void that extends in every direction for light years before encountering anything else of substance. Voyager 1 has now been traveling for nearly 5 decades. It has covered approximately 15 billion miles. It crossed the boundary of the heliosphere, the region where the sun's solar wind gives way to the interstellar medium, in 2012, becoming the first human-made object to enter interstellar space. And in terms of the distance to the nearest star, it has covered less than 1,000th of the way. In 5 decades of continuous travel, the fastest long-duration spacecraft ever built has made essentially no progress toward the nearest stellar neighbor. The gap is not merely large. It is large in a way that absorbs every human measure of speed and duration and renders them insufficient. This is the space between 2 stars, the nearest 2, the galactic equivalent of adjacent houses, as the analogy goes, though the analogy fails because no 2 houses have ever been separated by a gap that light needs 4 years to cross. And the Milky Way contains between 200 and 400 billion stars, each one separated from its neighbors by distances of roughly this magnitude, all of them distributed across a disk 100,000 light-years across. One gap between 2 stars is already beyond the reach of ordinary comprehension. Multiply it by hundreds of billions. Distribute those gaps across a structure larger than the mind can honestly picture, and what emerges is not a galaxy full of stars. It is a galaxy almost entirely made of the space between them. The stars are the minority. The silence is the majority. And across that silence, at this moment, the same emptiness extends in every direction, around every star, through every arm of the spiral, from the crowded center to the thinning edges, patient and vast, and indifferent to the small, warm things briefly burning within it. There is a thought experiment that cosmologists sometimes use when they want to convey the true scale of the Milky Way, and it goes like this. Imagine you could shrink the entire galaxy down to the size of North America. At this scale, the Milky Way's disk, 100,000 light-years across in reality, would span roughly the width of the continental United States, from the Pacific coast to the Atlantic. At this scale, our solar system, including the full extent of the Oort cloud, would be approximately the size of a single grain of sand, not a pebble, not a marble. A grain of sand, sitting somewhere in the middle of the country, roughly where Kansas or Nebraska would be, surrounded by hundreds of billions of other grains of sand distributed across the entire continent. And the average distance between those grains of sand, at this scale, would be roughly 2 to 3 miles. 2 to 3 miles between grains of sand across a continent. That is the Milky Way, not a crowded city of stars, not a dense field of light, a nearly empty continent-sized disk, scattered with grains, each grain separated from its neighbors by miles of open ground, the whole structure rotating slowly around a central mass that the grains will never approach in any meaningful human time frame. This is where we live. This is the structure our sun has been orbiting for approximately 4.5 billion years, completing perhaps 20 circuits of the galactic center in that time. drifting slowly through a neighborhood of other grains, each one as isolated as the next, each one burning its own brief fire in the silence between. The Milky Way's disk is approximately 100,000 light-years in diameter and roughly 1,000 light-years thick at the outer edges, thickening to perhaps 12,000 light-years at the central bulge. In our region of the galaxy, roughly 26,000 light-years from the center, in the Orion arm, the average distance between neighboring stars is approximately 4 to 5 light-years. This is not the distance between any two randomly chosen stars in the galaxy. It is the distance between nearest neighbors in a moderately populated region, the local average, and it is still 4 to 5 light-years, 20 to 30 trillion miles, of interstellar medium between any star and the next closest one. This is the regions of the galaxy. The spacing decreases. Near the galactic center, in the densely packed stellar environment surrounding the supermassive black hole at the Milky Way's core, stars can be separated by distances measured in light weeks, or even light days, rather than light years. A hypothetical planet near the galactic center would have a night sky blazing with nearby stars, far brighter and more numerous than anything visible from Earth. But even there, even in the most densely populated region of the galaxy, the stars are separated by distances that light needs days or weeks to cross. Days and weeks at 300,000 kilometers per second. The galaxy's densest region is, by any human standard of proximity, still incomprehensibly empty. The total stellar mass of the Milky Way, all the stars, all the gas, all the dust, all the stellar remnants, is estimated at roughly 50 to 60 billion times the mass of the Sun. That is an enormous number, but the volume of the Milky Way's disk is also an enormous number, and when you divide the mass by the volume, the result is a density so low it is difficult to express in familiar terms. The average density of matter in the galactic disk, integrated across all its components, is roughly 1 to 2 hydrogen atoms per cubic centimeter. Similar to the interstellar medium we discussed in the previous section, because the interstellar medium is, in large part, what fills the galaxy between stars. The galaxy is not a dense structure with a thin sprinkling of vacuum between objects. It is a thin structure with occasional dense objects embedded within it. To put this in human terms, if you gathered all the matter in the Milky Way, every star, every planet, every moon, every asteroid, every cloud of gas and dust, and distributed it uniformly throughout the galaxy's volume, the resulting density would be roughly equivalent to scattering a few dozen grains of sand across the entire volume of Earth's atmosphere. Not the surface, the entire atmospheric volume, from the ground to the edge of space. A few dozen grains of sand distributed through that space would represent the average density of the Milky Way. Everything else is void. This is the unusual. It is not a peculiarity of our galaxy. Spiral galaxies of similar size and type throughout the observable universe share roughly comparable densities, with variations that do not alter the fundamental picture. Galaxies are not dense structures. They are vast, diffuse, slowly rotating assemblies of mostly empty space, in which stars and gas and dust are embedded at low concentrations, separated by distances so large that the structures they form can only be perceived from outside, from distances so great that the individual components blur into the aggregate glow we call a galaxy. when we see one in a telescope image. The photograph of a galaxy. A spiral galaxy seen face on, its arms sweeping gracefully outward from a bright central core, the whole structure luminous and apparently dense, is a compression artifact. What the image shows is the accumulated light of hundreds of billions of stars, each one a point of light, each one separated from its neighbors by years of light travel time, all of them flattened by astronomical distance into a single glowing disk. The photograph lies in the same way the classroom model of the solar system lies. It makes the empty look full. It makes the isolated look adjacent. It turns a nearly empty continent into a dense and intricate pattern by removing the depth that makes the emptiness visible. The dark matter adds another layer to the picture. The stars, gas, and dust that produce the visible light of the Milky Way account for only a fraction of its total mass. The rest, approximately 85% of the Milky Way's total mass, by most estimates, consists of dark matter, a substance or a collection of substances that interacts with ordinary matter only through gravity, producing no light, no radiation detectable by any current instrument, no signal that any telescope has ever directly recorded. Its existence is inferred from the way the galaxy rotates. Stars in the outer arms orbit the galactic center, faster than the visible mass alone could account for, implying an additional unseen mass distributed in a vast halo surrounding and interpenetrating the disk. Dark matter is not dense. It is, if anything, even more diffuse than the ordinary matter it accompanies. The dark matter halo of the Milky Way extends far beyond the visible disk, reaching perhaps 100,000 light-years or more in every direction. A roughly spherical cloud of unknown particles drifting through the same space the stars occupy, interacting with nothing, leaving no mark. It passes through the Earth constantly, thousands of dark matter particles crossing your body every second, if the leading models are correct, without once interacting with any of the atoms you are made of. It is matter that behaves, for all practical purposes, as though it does not exist, as though the galaxy is even emptier than the stars suggest. The Milky Way is large beyond easy imagination. It is old, approximately 13 billion years, nearly as old as the universe itself. It has been forming stars for most of that time, consuming gas and dust and assembling it into burning spheres that live for millions or billions of years, before dying and returning their material to the interstellar medium. It is, in the most literal sense, a recycling system. Matter cycling from clouds to stars to supernovae to new clouds and new stars, over and over, across timescales that dwarf all of human civilization. And across all of that time, through all of that cycling, the fundamental character of the galaxy has not changed. It has always been mostly empty. It will always be mostly empty. The stars are a phase matter passes through briefly. The void is the constant. And the Milky Way, vast and silent as it is not alone. It sits inside a local group of roughly 50 galaxies, bound together by mutual gravity, drifting through space as a collection. The nearest large companion is Andromeda, 2.537 million light-years away, a spiral galaxy similar to our own, containing roughly 1 trillion stars, visible to the naked eye on a dark night as a faint smear of light in the constellation of the same name, 2.5 million light-years away. The light reaching your eye from Andromeda on a clear autumn night left that galaxy before the first members of the genus Homo walked the Earth. And between the Milky Way and Andromeda, across those 2.5 million light-years of space, lies a quality of emptiness that makes the interstellar medium feel almost welcoming. A void so complete, so uninterrupted, so devoid of any structure at any scale, that it requires its own name and its own category of consideration. The intergalactic void does not simply continue the pattern established by the interstellar medium. It deepens it, dramatically, in a way that, once understood, makes the galaxy itself, sparse as it is, silent as it is, seem like a warm and occupied place by comparison. There is a quality of darkness that exists between galaxies that has no name in ordinary language, because ordinary language developed in a world where that darkness was never encountered and never needed describing. Every word we have for dark, for empty, for silent, for alone, all of them were shaped by human experience, by nights under open skies, by caves and cellars and windowless rooms, by the felt absence of light or sound or company. None of them reach far enough. They are measuring cups being asked to hold an ocean. The intergalactic void is not the darkness between stars scaled up. It is a different category of absence. The interstellar medium, for all its emptiness, still has structure. It has phases, warm regions and cold regions, dense clouds and diffuse plasma, dust lanes and magnetic fields, and the occasional shock wave from a distant supernova. It is empty, but it is textured. It is vacancy with character. The intergalactic void has almost none of this. It is vacancy approaching the pure. It is the universe at its most honest, stripped of the local exceptions that make a galaxy or a star system feel like something, reduced to the baseline condition that the cosmos maintains across the overwhelming majority of its volume. The density of intergalactic space, the space between galaxies in a typical region of the universe, is approximately 1 atom per cubic meter. We visited this number briefly earlier in the night, but it deserves to be held for longer now. A cubic meter is a substantial volume. Picture a large cardboard box, roughly a meter on each side. Fill it, in your mind, with ordinary air, and you have placed approximately 25 million trillion molecules inside it. Now remove all but one hydrogen atom, drifting slowly in a cube of darkness the size of a large box, with nothing else nearby. Not for kilometers, not for light years, not for the distance to the nearest galaxy, which might be millions of light years away. That single atom is not surrounded by other atoms at comfortable distances. It is surrounded by nothing, in every direction, for a span of space that dwarfs anything the interstellar medium contains. The ratio between the air in a room and intergalactic space is not a large number, in the way that astronomical distances are large numbers. It is larger. The air contains roughly 10 to the power of 25 molecules per cubic meter. Intergalactic space contains roughly 1. The difference is a factor of 10 to the power of 25, a 1 followed by 25 zeros. If you wanted to write that ratio out in standard form and read it aloud, giving each digit 1 second, you would be reading for longer than the current age of the universe. It is not a number that fits inside any useful frame of reference. It simply is what it is, which is to say, The air around you and the space between galaxies are not 2 points on the same scale of density. They are, for practical purposes, incommensurable. This is the space that Andromeda sits across, 2.537 million light-years from the Milky Way. Light leaving the Andromeda galaxy today, carrying information about whatever is happening there at this moment, whatever stars are being born, whatever planetary systems are quietly orbiting their suns, will not arrive at the Milky Way for 2.5 million years. In the time that light spends crossing the intergalactic void between these two galaxies, it will pass through a region of space containing, on average, 1 hydrogen atom per cubic meter. For 2.5 million years of travel at 300,000 kilometers per second, the photon will encounter almost nothing. It will cross a distance of approximately 15 quintillion miles, that is a 15 followed by 18 zeros, through a medium so sparse that the photon has essentially no chance of interacting with any particle along the way. It will arrive, if it arrives, having experienced the crossing as a journey through pure vacuum. Consider the local group itself, the roughly 50 galaxies bound by mutual gravity into a single gravitational system, spanning approximately 10 million light-years in its longest dimension. 10 million light-years sounds like a densely packed collection of galaxies. But 50 galaxies distributed across a volume 10 million light-years across occupy that volume at a concentration so low that the average density of galaxies within the local group is roughly 1 galaxy per 200 cubic million light-years. Each galaxy is a tiny island of matter, isolated from its nearest neighbor by millions of light-years of intergalactic void, connected to the others only by the slow, invisible pull of gravity, operating across distances that light needs millions of years to cross. There is a night sky that no living thing has ever seen, and it belongs to any world that might exist in the deep intergalactic void, not inside any galaxy, but in the space between them. Such worlds are thought to exist, ejected from their home galaxies by gravitational interactions, drifting alone through intergalactic space for billions of years. Planet in the intergalactic void would orbit no star. It would receive no starlight. Its sky, on any night, would contain no nearby stars, no Milky Way stretched across the darkness, no Andromeda smear visible to the naked eye. The nearest galaxy might be millions of light-years away, a faint smudge in a telescope, if any instrument existed to point at it. The sky would be effectively black, not the black of a moonless rural night, with its thousands of visible stars and its band of galactic light. A deeper black, a black with almost nothing in it. The universe at its most typical, the universe as it mostly is. You are not on such a world. You are on a world that sits inside a galaxy, in a moderately populated stellar neighborhood, bathed in the light of a nearby star, surrounded by planets and moons, and the accumulated debris of 4.5 billion years of solar system history. You are, by the standards of the universe, in an extraordinarily dense and fortunate location. The warmth you feel, the air you breathe, the light by which you read or the voice you are hearing, all of it is the product of a local density anomaly, a small violation of the universe's overwhelming preference for emptiness, occurring in a thin shell of atmosphere on a small rock, which orbits a star, which drifts through a galaxy, which sits in a local group, which is embedded in a larger structure still. Each layer is denser than the void surrounding it. Each layer is, by the standards of the void, a miracle of concentration. the intergalactic medium is not entirely without structure. It is threaded, at very large scales, by magnetic fields too diffuse to measure directly, but inferred from their effects on cosmic ray particles crossing the void. It contains traces of gas, hydrogen and helium, the same elements that fill the interstellar medium, but at densities even lower than the 1 atom per cubic meter average in many regions. It carries the warm-hot intergalactic medium, a diffuse plasma of gas heated by ancient shocks and gravitational compression to temperatures of tens of thousands of degrees, a gas so thin that its total thermal energy is negligible. Its temperature, a statistical property of particles separated by distances so large they almost never interact. Hot, in the sense that the individual particles move quickly. Cold, in the sense that there are so few of them that no warmth is transferred to anything. This is one of the stranger facts about the intergalactic void. It is, in places, technically hot. Particles moving at speeds consistent with high temperatures, and simultaneously, experientially, the coldest environment imaginable, because temperature, as a felt phenomenon, requires particles dense enough to collide with other matter, to transfer energy, to warm a surface. In intergalactic space, the particles are too few and too far apart to warm anything. A thermometer placed in the intergalactic medium would not register the technical temperature of the plasma. It would register something close to absolute zero, because almost nothing would ever strike it. The void is not merely empty. It is empty in ways that ordinary emptiness cannot accommodate. It is empty at the level of heat and cold, of sound and silence, of presence and absence. It is the universe's resting state, not a temporary condition waiting to be filled, but the permanent, dominant, overwhelming character of space at the largest scales. And even this, the intergalactic void, with its single atom per cubic meter, its near absolute cold, its millions of light years of uninterrupted darkness, is not the largest empty structure the universe contains. Because when we pull back further still, to the scale at which galaxies themselves become small, a pattern emerges in the distribution of matter that makes the intergalactic void between individual galaxies look, by comparison, almost intimate. The universe, it turns out, is organized around its emptiness. The voids are not the spaces between the structure. The voids are the structure, and they are larger than anything else the universe has built. If you could somehow rise above the observable universe, step outside it, look down at it from a distance great enough to take in its full extent, what you would see would not look like a field of galaxies scattered randomly through space. It would not look like a uniform fog of light, or a smooth gradient of density, or anything that simple. What you would see, if the simulations and the observations are correct, is something that looks remarkably like the interior of a sponge, or the foam that forms on the surface of a wave, or the tangled web of a spider working at the largest scale anything has ever worked at. Vast, dark, rounded voids, regions of space nearly devoid of galaxies, separated by thin walls and filaments of matter, along which galaxies are strung like faint beads on an almost invisible thread. The structure is ancient. It was seeded in the first moments after the Big Bang, when tiny quantum fluctuations in the density of the early universe were stretched to cosmic scales by a period of rapid expansion, imprinting a pattern on the distribution of matter that gravity has been amplifying ever since. Over 13 billion years, matter has been slowly draining out of the voids and accumulating along the filaments, thickening the walls, brightening the nodes where filaments intersect, and deepening the darkness of the voids themselves. The result is what cosmologists call the cosmic web. And the cosmic web is, above everything else, a structure organized around its own emptiness. The filaments and walls that make up the web's visible scaffolding are themselves not dense. A galaxy filament is a region of somewhat elevated galaxy density, more galaxies per unit volume than the surrounding voids. But the galaxies within a filament are still separated by millions of light years of intergalactic space. The filament is a relative concentration, not an absolute one. It is denser than the void, the way a thin mist is denser than perfectly dry air. Both are, by any meaningful standard, mostly empty. The difference between them is a difference of degree, not of kind, and the degree is not large. The voids are something else entirely. Cosmic voids, the rounded dark regions that make up the interior of the sponge, are the largest discrete structures in the observable universe. They range in size from tens of millions of light years across to several 100 million light years, and they are, within their boundaries, almost completely devoid of galaxies. Not entirely. Void regions contain small numbers of galaxies. The occasional isolated dwarf galaxy, the rare small group, but at densities so far below the cosmic average that the voids register on large-scale maps of galaxy distribution as near absolute darkness. The matter that should be there, by a uniform distribution, has drained away. Gravity pulled it outward over billions of years, toward the filaments and walls at the void's edges, leaving the interior emptier than it was at the beginning. The voids are growing emptier over time, not fuller. As the universe expands and matter continues to flow toward the web scaffolding, the voids deepen. The darkness at the center of a void today is darker than the darkness at its center a billion years ago, and it will be darker still a billion years from now. The most famous individual void has a name, the Boötes void. It was discovered in 1981 by astronomer Robert Kirshner and his colleagues, who were conducting a survey of galaxy redshifts, a method of measuring how fast galaxies are moving away from us, which also indicates their distance. When the data from a particular region of the sky came back, a gap appeared, a region roughly spherical in shape, centered in the direction of the constellation Boötes, containing almost no galaxies across a diameter of approximately 330 million light-years. In a universe where galaxy clusters and groups are found almost everywhere the survey reached, here was a hole, a volume of space 330 million light-years across, containing, at the time of discovery, only a handful of galaxies, where statistical expectations suggested there should be thousands. 330 million light-years. To cross the Boötes void at the speed of light, traveling in a straight line from one side to the other, would take 330 million years. In that time, on Earth, the Permian-Triassic extinction event would occur, the dinosaurs would rise and fall, the mammals would diversify, the primates would emerge, the genus Homo would appear, and all of recorded human history would unfold, multiple times over. The crossing would require 330 million years at the fastest speed the universe permits. And for the entirety of that crossing, in almost every direction, there would be essentially nothing to see. No galaxy clusters, no bright nodes of the cosmic web, no concentrations of stars dense enough to resolve as anything other than the faintest possible background, just the darkness of the void and the slow recession of the walls on either side, and the near absolute quiet of intergalactic space, uninterrupted for a distance that comprehension cannot honestly reach. What would it mean to live inside the Boötes void? Not on a planet inside a galaxy near its edge, where the void's boundary might be visible as a region of unusual darkness in one direction. Inside, in the deep interior, where the nearest galaxy cluster might be 100 million light-years away in every direction. The night sky of such a world would be almost empty of the structures we associate with the universe. The cosmic web's filaments, the clusters and groups and superclusters that define the large-scale structure of the observable universe, would be absent from the visible sky. The nearest galaxies would be so distant that they would require a large telescope to detect at all, appearing only as the faintest smudges in the deepest exposures. The universe, from that vantage, would appear to be almost entirely empty, not because it is unusual, but because the vantage is honest. Because from inside a void, the universe looks the way it mostly is. From our position on Earth, inside the Milky Way, inside the local group, embedded in the larger Laniakea supercluster, a structure of galaxies spanning roughly 500 million light-years, of which we occupy an outer region, the universe looks populated. Galaxies are visible in every direction. The cosmic web's filaments are detectable in the distribution of galaxy redshifts. The universe, from here, appears to have texture, to have structure, to be full of things. But this is a location bias. We are in one of the denser regions of the cosmic web, near the intersection of filaments, in a gravitational environment that has accumulated matter over billions of years. We see a populated universe because we are in a populated corner of it. The Boötes void sees a different universe, the majority universe, the typical one, and it is nearly empty. The total fill fraction of the observable universe, the ratio of the volume occupied by matter-containing structures to the total volume of space, is difficult to calculate precisely, but estimates consistently place it below a few percent. Some analyses suggest that cosmic voids account for roughly 80 to 90% of the universe's total volume. The filaments, walls, and clusters of the cosmic web, all the structure visible in the large-scale surveys, all the galaxies and groups and superclusters, occupy the remaining 10 to 20%. And within that 10 to 20%, most of the volume is still intergalactic space. The galaxies themselves, the dense concentrations of stars and gas, fill a tiny fraction of even the web's scaffolding. The universe, at the largest scale of examination, is a thin foam of matter surrounding enormous bubbles of almost nothing. The bubbles are the majority. The foam is the exception, and the foam itself, examined closely, dissolves into more emptiness. The intergalactic voids between galaxies, the interstellar voids between stars, the atomic voids between nuclei, all the way down to the quantum vacuum at the floor of reality. Emptiness at every scale. Emptiness as the organizing principle. Matter as the rare and temporary departure from the rule. This is what the universe is made of. Not stars, not galaxies, not the dramatic structures that populate our images and our imagination. The universe is made of emptiness, organized into patterns by gravity, punctuated at rare intervals by the brief warmth of matter. The structures are real. The stars burn and the galaxies rotate, and the filaments of the cosmic web stretch across hundreds of millions of light years. But they are the decoration. The void is the canvas, and the canvas is almost everything. What this means for matter, for chemistry, for the possibility of life arising anywhere in this near-empty cosmos, is a question the universe does not answer easily. Because life, whatever else it requires density. It requires proximity. It requires atoms close enough to bond, temperatures stable enough for liquid to persist, energy sources consistent enough for chemistry to proceed across the billions of years that complexity demands. And the universe, as we have seen it tonight, is not generous with density. It withholds it. It distributes it in thin threads and rare nodes, separated by voids so vast that the threads themselves are barely there. Life, if it exists anywhere in the structure, exists in the margins, in the narrow, improbable places where the universe has briefly, locally, relented from its preference for emptiness and allowed matter to gather close enough to do something interesting. And somewhere in those margins, something did. Life, as far as we know it, requires a very specific set of conditions. Not rare conditions necessarily. The universe may produce them in many places, but conditions that are, by the universe's own standards, extraordinarily unusual. Liquid water, a stable energy source, a temperature range narrow enough that complex molecules do not shake apart, chemical environment rich enough in heavier elements, carbon, nitrogen, oxygen, phosphorus, sulfur, that the intricate molecular machinery of biology can assemble itself. A timescale long enough, measured in billions of years, for that machinery to develop from simple chemistry into something capable of reproducing and evolving. Every one of these requirements is a condition that the universe, across the overwhelming majority of its volume, simply does not meet. Consider temperature first. The cosmic microwave background, the faint thermal radiation left over from the early universe, now cooled by 13 billion years of expansion, gives the universe a baseline temperature of approximately 2.7 degrees above absolute zero. That is the temperature of empty intergalactic space, the temperature of the void at its most typical. Absolute zero is the point at which molecular motion ceases entirely, the lowest temperature physically possible. The universe's baseline sits just 2.7 degrees above that floor. In practice, this means that the overwhelming majority of the universe's volume is too cold for liquid water to exist, too cold for almost any chemistry to proceed at a meaningful rate, too cold for anything recognizable as life to maintain itself against the thermodynamic pressure toward disorder. Life requires warmth. The universe is almost entirely cold. The warmth is local, temporary, and entirely dependent on the proximity of a star, itself a rare concentration of matter in an otherwise sparse distribution. Consider chemical composition. The two most abundant elements in the universe are hydrogen and helium, together accounting for roughly 98% of all ordinary matter. Carbon, the element on which all known life is based, the backbone of every organic molecule, the atom whose bonding flexibility makes biological complexity possible, constitutes roughly 0.5% of ordinary matter by mass. And even this small fraction is not uniformly distributed. Carbon and the other heavy elements life requires are produced inside stars through nuclear fusion and distributed through the galaxy by supernova explosions. A region of the universe without stars, without the recycled material of previous stellar generations, without the slow enrichment of the interstellar medium by repeated cycles of star formation and stellar death, would lack the chemical raw materials for life entirely. Most of the universe's volume, the intergalactic voids, the vast dark spaces between galaxies, is composed almost entirely of primordial hydrogen and helium. Not because chemistry hasn't happened there, but because the stars that produce heavier elements have never been present in sufficient numbers to enrich the void. Life, then, is doubly constrained. It requires density for proximity and chemistry, and it requires a specific location within the cosmic web, inside a galaxy, near stars of the right type and age, in a region enriched by multiple generations of stellar evolution. It requires not just any matter, but the right kind, assembled in the right place, at the right time in the universe's history. The universe has been producing the right conditions for life only in its dense corners, its filaments and galaxy clusters, its local groups and stellar neighborhoods. The voids do not participate. Most of the universe, by volume, is not a place where life as we understand it could arise. And yet within the corners where conditions are met, the numbers are not small. The Milky Way alone contains between 200 and 400 billion stars. Of those, a substantial fraction, estimates vary, but many astronomers consider it likely that the majority of sun-like stars host planetary systems, are orbited by planets. The fraction of those planets that fall within the habitable zone of their star, at distances where liquid water could persist on a rocky surface, is smaller but not negligible. Extrapolating from the exoplanet surveys conducted over the past few decades, there may be billions of potentially habitable worlds in the Milky Way alone. Billions of worlds where the temperature is right, where liquid water could exist, where the chemistry of life is at least not forbidden. This sounds like abundance, and in absolute terms, it is. But set against the scale of the universe we have been describing, against the hundreds of billions of galaxies in the observable universe, each containing hundreds of billions of stars, all of them concentrated in the thin 10 to 20% of cosmic volume that the Webb's scaffolding occupies. The number of potentially habitable worlds is also a measure of isolation, because each of those worlds is separated from every other potentially habitable world by the same interstellar and intergalactic distances we have spent this night examining. The existence of billions of potentially habitable planets does not mean those planets are close to one another. It means they are distributed, one by one, across the same vast and empty galaxy, separated by the same light years of interstellar medium, the same spans of vacuum that no spacecraft we can build could cross in any meaningful human time frame. Life in a nearly empty universe is not merely rare by circumstance. It is isolated by structure. The emptiness that surrounds every potentially habitable world is not incidental to its situation. It is the defining fact of its situation. Whatever lives on a world around Proxima Centauri, if anything does, and the question remains genuinely open, is separated from whatever lives on a world around the next nearest star by the same 4 or 5 light years of interstellar void that separates those stars from us, and from the next world after that, and the next. Each island of potential life floating in its own portion of the void, close enough to other islands to detect them, in principle, cross the darkness, but separated from them by distances that make physical contact nearly impossible and communication measured in years at the very best. The universe is not hostile to life. Hostile implies intent, and the universe has no intent. It is simply structured in a way that makes life's requirements difficult to meet across most of its volume, and that separates the places where those requirements are met by distances so large that the life arising in those places may never know about the life arising in any other. This is not a tragedy in any dramatic sense. It is simply the arithmetic of a nearly empty cosmos. The emptiness does not hate life. It does not notice life. It surrounds life with the same indifference it extends to everything else, to the stars, to the galaxies, to the filaments of the cosmic web, to the dark matter drifting through every structure without touching any of it. You are listening to these words on a world that has spent 4 billion years becoming hospitable to the kind of chemistry that eventually produced something capable of listening. 4 billion years of geological and biological process, of star-forged elements assembling and reassembling, of evolution selecting and discarding, of climate stabilizing and destabilizing and stabilizing again. All of it occurring in a thin shell of atmosphere on a small rocky planet, orbiting an ordinary star, in a moderately populated region of a spiral galaxy, embedded in a local group, threaded through a supercluster, surrounded in every direction by the same void we have been describing all night. The conditions for your existence are, by the universe's standards, a local exception so improbable that no single number can express its rarity, and they are occurring right now in this thin and temporary pocket of density and warmth, while around it, in every direction, to distances that take millions of years to cross at the speed of light, the universe maintains its default condition: cold, dark, empty, patient. The emptiness does not end at the edge of the atmosphere. It does not end at the edge of the solar system, or the galaxy, or the local group. It extends in every direction across scales we have spent this entire night attempting to convey, through every structure and every void, to the farthest reaches of the observable universe and presumably beyond. It is not waiting to be filled. It is not a temporary condition that the universe will eventually overcome. It is what the universe is. It is what the universe prefers, if preference can be said to apply to something with no awareness of its own nature. And somewhere in it, in this one small corner, on this one small world, in this one thin moment of cosmic time, something became aware of the emptiness surrounding it. Something looked out and tried to measure what was there, and found, after centuries of careful looking, that what was there was mostly nothing, and found, after sitting with that for a while, that the nothing was not terrifying in the way that the first encounter with it suggested, that it was simply the context, the frame around the small, warm, improbable picture. The picture is still there. You are still in it. The darkness around it is vast, beyond any word you have for vast. And it has been there since before the picture existed, and it will be there long after the picture fades. But for now, in this brief interval, the picture is lit. Something is here. Something is aware. And in a universe this empty, that is not nothing. That is almost everything. There is a photograph taken on September 5th, 1977, the day Voyager 1 launched from Cape Canaveral. In the photograph, the rocket rises on a column of fire and smoke, climbing away from the Earth into a pale Florida sky. The rocket is bright. The sky around it is blue and full of light. The Earth below is green and warm and present. It is a photograph of departure, of something small leaving something large, of a human-made object beginning a journey outward into the solar system and beyond. At the moment that photograph was taken, no one alive could have fully understood where Voyager 1 would eventually go, or what it would eventually tell us about the place it was leaving behind. In February of 1990, 13 years into the mission, the spacecraft turned its camera backward. It was approximately 3.7 billion miles from the Sun, already beyond the orbit of Neptune, already in the outer reaches of the solar system, already in a place no human-made object had ever been. The camera was old by then, and the image it produced was grainy, washed with scattered light from the sun, barely adequate for the task Carl Sagan had been advocating for years, the task of looking back. In the resulting photograph, Earth appears as a pale blue dot, a point of light smaller than a single pixel, suspended in a broad shaft of sunlight against a background of absolute black. No features are visible. No continents, no oceans, no clouds. Just the dot and the darkness and the beam of light catching the planet, the way a beam of light catches a mote of dust, drifting through a quiet room. Everything you have ever known is in that dot. Every person who has ever lived, every city ever built, every ocean ever sailed, every mountain ever named, all of it occurring on a speck of matter so small that the camera almost missed it entirely, surrounded in every direction by the emptiness we have been describing all night. The solar system's void stretching outward from the dot in every direction. The interstellar medium beginning where the solar wind fades. The galaxy continuing for 100,000 light-years beyond that. The intergalactic void opening beyond the galaxy's edge. The cosmic web's filaments and voids extending to the observable horizon. All of it dark. All of it cold. All of it almost perfectly empty. And in the center of a frame that could contain all of this, pale blue dot barely there, carrying everything that has ever mattered to anything that has ever been capable of mattering. This is not a melancholy image. It was not intended as one, and it does not need to be received as one. It is simply an honest image. It shows the universe at something closer to its actual proportions than any photograph taken from the surface of the Earth can manage. From the surface, the Earth feels large. The sky feels full. The stars feel close. From 3.7 billion miles out, still well within the solar system, still an immense distance from the nearest star, the Earth is a dot, and the feeling of largeness is revealed as a local artifact of proximity. The universe is not large and full with a few empty patches. It is empty with a few small and temporary points of warmth. You are one of those points of warmth, a brief concentration of matter and energy, arranged into a pattern, complex enough to be aware of itself, located on a pale dot in the outer arm of a spiral galaxy, listening in the dark to words about the darkness surrounding you. The atoms in your body were forged in the cores of stars that died before the sun existed. They drifted through the interstellar medium for millions of years before being gathered by gravity into the cloud that collapsed to form the solar system. They assembled over 4 billion years of chemistry and biology into the structure that is currently breathing slowly and listening to this. When you are done with them, they will return to the interstellar medium eventually, and drift again, and be gathered again, and assemble into something else. The atoms are old, the arrangement is temporary, and both of these things are true at the same time, without contradiction. The universe has been expanding since the moment of its origin, approximately 13.8 billion years ago. It will continue expanding. The expansion is accelerating, driven by the dark energy that fills the void between galaxies and pushes space itself outward at an increasing rate. As the expansion continues, the voids grow larger. The filaments of the cosmic web thin further. Galaxies outside the local group are already receding from us faster than light can cross the growing distance, placing them beyond any future contact. Over billions of years, the galaxies now visible in our night sky will redshift beyond detectability, their light stretched by expansion until it falls below any frequency we could observe. The observable universe will shrink, not because it is contracting, but because the light from distant galaxies will no longer be able to reach us across the growing void. A civilization arising in the far future, billions of years from now, if any such civilization exists, will look out at a sky containing only the local group. The rest of the universe will have receded beyond observation. They will see a smaller cosmos than we see, not because the universe is smaller, but because the emptiness will have grown too large to see across. The darkness will have won, not dramatically, not suddenly, but gradually. The way darkness always wins, by outlasting the light, by expanding while the light remains fixed, by being patient in the way that only truly vast and indifferent things can be patient. The stars themselves are temporary. The sun has approximately 5 billion years remaining before it exhausts its hydrogen fuel, expands into a red giant, and eventually collapses into a white dwarf, a faint, cooling ember the size of the Earth, slowly radiating its remaining heat into the surrounding void. The more massive stars burn faster and die sooner. The less massive red dwarfs burn slowly, some of them lasting trillions of years, but they too will eventually cool and darken. Given enough time, more time than the current age of the universe by factors that have no useful analogy, all the stars will go out, the galaxies will fade, the matter that remains will decay slowly across timescales so vast that the current age of the universe is less than a single second in comparison, and the universe will return, fully and finally, to the condition it has maintained across most of its volume for most of its existence. Cold, dark, empty. This is not a thought designed to disturb sleep. It is a thought designed to locate the present moment honestly within the full span of what exists. Right now, in this brief interval of cosmic time, the stars are burning, the galaxies are bright. Chemistry is occurring on small warm worlds scattered through the web's thin scaffolding. Something is listening to these words in the dark, breathing slowly, on a planet that still has a sun. The emptiness is vast, and it is patient, and it surrounds everything, but it has not yet finished its work here. The warmth is still present. The light is still traveling. And somewhere in the silence between the galaxies, between the stars, between the atoms of every solid thing, the void waits with the particular patience of something that has always been the majority and always will be. It does not press. It does not hurry. It simply extends in every direction, at every scale, from the quantum floor of reality to the outermost reaches of the observable universe, consistent and permanent, and indifferent and enormous. You are a brief density in it, a temporary gathering of matter in a universe that prefers dispersion. A small, warm, aware exception to the rule that everything is empty and cold and dark. The rule has not been broken. It has been, for a moment, suspended. Here, now, in this thin and improbable place. And for now, that is enough. You are listening to these words in a room somewhere, a room with walls and air, and the faint sounds of whatever world exists just outside it. The room feels solid. The walls feel present. The air feels full. Everything in your immediate experience conspires to suggest that the universe is a populated and generous place, full of matter and warmth, and the comfortable density of things close enough to touch. And it is here, in this room, on this world, in this one small corner of a structure so vast and so empty that the room, the world, the entire solar system, the galaxy itself, all of it together, barely registers as a deviation from the norm. The terrifying truth the title promised is not a fact you can hold in your hands. It is not a number, though the numbers point toward it. It is not a distance, though the distances confirm it. It is something quieter and more permanent than any of those things. It is simply this: the universe is not full of matter with emptiness between it. It is full of emptiness with matter briefly, locally, improbably gathered into structures we have given names to. The names are real, the structures are real, but they are the exception. The emptiness is the rule, and the rule extends without interruption in every direction, to every horizon, at every scale. Picture a single candle burning in a very large room. The candle is real. Its light is real. The warmth near its flame is real. And if you sit close enough, you can feel it. But the room is large. Larger than any room you have ever been in. Larger than any room you can picture. Larger than the word large was designed to describe. And the darkness that fills the room beyond the candle's reach is not the absence of something that should be there. It is what the room is made of. The candle is the visitor. The darkness is the host. You are the candle. This world is the candle. Every star in every galaxy, in every filament of the cosmic web is a candle, burning briefly in a room of almost incomprehensible size and darkness, casting light across a tiny sphere of space, surrounded on every side by the void that was there before the candle was lit, and will be there long after it goes out. This is not a reason for despair. It is a reason for the particular kind of quiet that comes from understanding your own location honestly. You are here. You are warm. You are, against all the odds, the universe has stacked against the existence of anything at all, briefly and improbably present. The universe is vast and dark and almost entirely empty. And somewhere inside it, right now, something is aware of that.